So, I just want to say, actually, someone asked me a question, and I just want to, I think it's a really good point, so I want to just elaborate on it a little bit. So somehow, you know, everyone who sees this definition of the universal Teichmüller space for the first time, they somehow feel this is crazy, because, okay, the disk, the Riemann moduli space is a point. So what are you going on about that you're going to have this infinite dimensional space of parametrization for the Teichmüller space? And this is a really natural reaction. And so I honestly do not have a great answer for why this space was invented, and including the general Teichmüller spaces, why it was invented by historically. I have some guesses about it, but I'm no historian, so I can't say. But I want to say my own take on it. I'll say two things. So first thing is that Teichmüller space is not actually a space of about one surface. It's about how one surface sits in another one. So when you do conformal welding, this is just in case you know about conformal welding, you can think of this space as being the different embeddings of the circle into the sphere. So it's somehow a relative object. And so I've actually been obsessed with that idea since I was a graduate student. And Wolf Staubach and I wrote a survey on this point of view in function theory and Teichmüller theory. And and I also think it's implicit in CFT. So this is something that really helps me understand what the Teichmüller space is. The other thing I want to say about it is I suspect that the reason that it was invented, again, I haven't done a historical study. Maybe somebody who knows it better, I'd love to talk about this. But I think that when you start thinking about holomorphic motions, you're somehow led inevitably to deformation of things in the plane. And if you, essentially there's a theorem that says any holomorphic deformation is quasi-conformal. So you end up forced to be thinking of these kinds of things. The other thing is there's some general theorems due to Earl and Fowler, which show that there's this Teichmüller curve that sits above Teichmüller space, and there are some theorems that this is universal in the sense that any holomorphic motion of a Riemann surface embeds into this Teichmüller curve. So if you do it this way, you end up, after a bit more work, again, due to Burrs, and then later completed by Earl and Fowler in a very nice, satisfying way, you end up with a universal space that contains all the deformations. By the way, that universality is not the same universal word as the universal Teichmüller space. There is a universality property of the Teichmüller curve over for any type surface. So if you do this, you get a bunch of natural things, and also remarkably the Segal moduli space. So this, I don't know, I find this, I still think about this. And I'll bring this up again in a minute when I talk about the Burrs embedding. So, okay, what are we going to do? There's a space of quadratic differentials here, which is a nice Banach space. And what we're going to do is we're going to put the Teichmüller space in the space of quadratic differentials. So there's this thing called Burrs trick. So take mu in L infinity minus 1, 1 of dg, and actually I'll take it in the equivalence class, and then take a representative. It turns out to work. We solve the Beltrami equation. Now, what we do, we take it from mu hat, should be mu on d minus and 0. Oops, sorry, this should have a minus there. On d. So, so we find f hat L such that d bar f hat L over dfL is equal to this mu hat. I'm calling it f hat L because it's the lift of, so FL lifts some, or FL is a solution on D minus with the mu. So in the old days, what people did initially is they, well, it was all the old days, they would reflect in the boundary and get what's, get a Beltrami differential, and then you get what's called the real analytic Teichmüller theory. And if you do this Burr's trick, you get what's called the complex analytic Teichmüller theory. And what happens now is you have that F hat L restricted to the disk is now conformal. So now the Burr's embedding, I wonder if I can fit it here. So beta takes the Teichmüller space of the disk mod G into A2 infinity of D plus, or sorry, just D mod G. And so what you do is you take your equivalence class of mu's, and then you map it to the Schwarzian of F at L restricted to the disk. So let me make some remarks about this. In the background, if you don't like the mu model, you can think of this mu as coming from some, you know, I'll just leave it like that. I can fill in if anyone has questions. Okay, any questions about the definition? It's pretty implicit, so this is a good place to pause, and maybe if you want to pick it apart, I can explain things. If anyone's...
You can draw a picture.
Okay. Okay, how about I draw a picture in the case of just the disk? We remove the group invariance, okay? So now what we have, so forget about the group invariance. We take a deformation of the disk. And actually this is where conformal welding comes in. It's in the background here. So you have some quasi-conformal map. And then you solve d bar f hat, df hat is equal to, we need this new mu hat, which is the Beltrami differential of f on d minus and 0 on d. So then that means what you get, this is now a quasi-conformal map of the whole sphere. And it now takes the disk conformally onto some what's called a quasi-circle. That's an image of the circle under a quasi-conformal map. So you get actually some nice map here. F hat restricted to D is conformal. Okay? So this over here is just the group invariant version. And then you take the Schwarzian of that, and then, okay, maybe a silly way to think about it, I don't know how silly it is, but one way to think about it is you mod out by the Mobius transformations, because the Teichmüller equivalence relation does. So we take the Schwarzian to mod out by the Mobius transformations. So okay, and okay, I want to just pause for a second here. No, let me say the theorem first. And eta is well defined, which means if you take two different f's that are equivalent, you get the same f hat restricted to the disk. So now all that arbitrary extension of the quasi-conformal map goes. It's all killed by taking this burst trick and taking the Schwarzian. It's also injective. And now here's maybe the most important thing, is it maps the Teichmüller space homeomorphically onto an open disk or open set. In A to infinity of VG. I'm mixing my lifted picture and my non-lifted picture, so let me just write this as D minus mod G. Okay. So now we've embedded this complicated space of quasi-conformal deformations into a Banach space of nice holomorphic objects. And that's called the Burrs embedding. And this is how you get the complex structure, because you just pull it back, pull the nice Banach. It's one of the ways to get the complex structure. There's a half dozen. You just pull it back to the Teichmüller space, and that's your definition. Okay, so let me make a few comments. So this I'm going to stop and go on to the Segal moduli space. Are there any questions up to here?
Is it an easy calculation to see that this is the Schwarzian of a conformal map is always a quadratic differential? Homomorphic quadratic differential?
Yeah, that's a good question. I mean, actually, this is kind of, there's a complicated version of your answer, which is, what do you mean by the derivative on a Riemann surface? So if I stick in the disk, I can avoid this question. But in general, first derivative is going to be something like f prime dz. Second derivative is going to be something like f double prime dz squared, f triple prime dz cubed. And then there's a calculus of these n differentials, and then it has to be a quadratic differential.
Yeah.
Okay, that's actually the complicated version, because even that, if you think very hard, the definition of a higher order derivative requires the choice of a metric. This is something I thought about in my thesis and is not published in a couple of papers. So it's actually, I think your question is very subtle. Okay, but then an easy version of your question is, well, if we're going to think about, how things transform under a Fuchsian group, then that's just a simple computation. Okay, so, yeah. But that's, I think, not quite the same question as you were asking.
Any other good reason why the Schwarzian derivative works here? It appears in so many places.
Yeah, I mean, it's okay. So David Minda, who was my external advisor, said the Schwarzian is too invariant. So it comes up in all these situations because it's so invariant. It's got so many properties that it just keeps coming up. And I don't know if that's a good reason or not, but I mean, I think there's a lot of answers to your question. Some of it has to do with projective structures. So I think that's what's going on in the background. But then actually, if you go into the Segal picture, then it's actually, the Schwarzian's not enough to say what's going on. I probably won't get there today, but maybe in a couple of weeks. So, okay, now I want to say something that I think is really, I find this really remarkable, that you have this space of deformations of complex structures, and then through this trick, it's identified with a space of symmetries of a fixed complex structure. Right? You're looking at, this Burrs trick embeds quasi-conformal deformations, identifies them with conformal symmetries of a fixed structure. I think this is really deep, and I think it's this beauty of this Burrs trick that, anyway, it's one of these.
Question related to that, because I have this double here. So
Yeah.
am I correct to say that this construction that you gave, it actually identifies the Teichmüller space with quadratic differences on the double.
That's exactly what happens. I was going to write that down, but I was thinking I was running out of time. But yeah, that's exactly right. So then you could write another version of the Burrs embedding like this. You could say Burrs embedding takes Teichmüller space of sigma into a to infinity of the double. What do I say here? Sigma star. And then what you do is you just take, mu on sigma now is going to map to, you push down, let's call this B sigma. You push down the quadratic differential on upstairs under your beta. And that's well defined by the invariance. So this is actually something I really should say, is that invariance here makes the output Schwarzian invariant, which is, I embedded it into this theorem when I said well defined, but that another way of interpreting is exactly what you said. Any other questions or observations? Okay, so now, Segal moduli space. What's the official end time? What is the end time which will not make everyone
Coffee
feel
at
ready?
4, so maybe people want to go.
So
Yeah, coffee at 4, so that's when people want to go. But.
okay. Yeah, I guess I'm old-fashioned. I'm used to like start and end times. So I need to know. So let me start with the rigging regularity. I don't know if I like the term rigging, but I guess I've seen it in some places, and I got it from David. So we're now back in the Segal moduli space picture. Before I state it, I just want to talk about the possible regularity choices. So you can look at analytic diffeomorphisms of the circle, so restrictions of analytic or conformal maps of an annulus to the circle, the ones that particularly preserve the circle. And that sits inside diff S1, the smooth ones. That sits inside the Weil-Petersson quasi-symmetries, which I'll talk about, hopefully, I should talk about next time, I'll make sure I do. So you have this chain of inclusions, and each one is a strict inclusion. So you have some choice here in the Segal moduli space, what you're going to parameterize by. So, I'm going to use, so these are sort of the customary ones in CFT, but I'm going to use this one in order to make the connection with the Teichmüller space. So here's the definition of the Segal moduli space. So M tilde B of Gn is the set of sigma B mod an equivalence relation where we say here, so sigma is genus G Riemann surface with n borders. homeomorphic to S1. So this is the picture. And phi is a set of parametrizations. Why am I bending over? We actually assume that the Riemann surfaces have ordered boundaries. I should have said that before I wrote this previous line. And now I have to define this equivalence relation. You say that sigma phi is equivalent to sigma prime phi prime if and only if there exists a sigma which is conformal such that, let's see, phi prime goes here. So phi prime is equal to sigma of phi for all k. Okay? So in brief, you have Riemann surfaces, but also with some boundary parametrization, and you want the boundary parametrization to be preserved by or to be not modded out by the equivalence relation. So the only difference from the usual Segal moduli space is that we're allowing them to be quasi-symmetries instead of just merely smooth. B here stands for the border model, and then there's equivalent puncture model. So I have to do a little bit of preamble before I say the puncture model. Is there any questions though about this?
Thinking now back to the Teichmüller space, if there also somehow the borders were ordered already implicitly.
That's a good point. Yeah. So what happens is, if you think of that quasi-conformal marking map, so because of the homotopy-Rel boundary condition, you somehow, that determines an order on your boundary. So if you put one on the base surface, then you get an order on the image surface. However, your question is important when you want to go to the Riemann moduli space. I haven't got there yet, but I mod out by a little bit too small a group to get down to Riemann. And you have to allow interchange of borders to do that. But anyway, yeah, short answer to your question, the quasi-conformal marking map orders the boundaries. So it's somehow, it's implicit there. Any other questions? Is it hot in here? I mean, I know I'm standing up, so maybe I'm hotter than everybody else, but does anyone?
It's area dependent.
What's that?
It's area dependent.
Okay, so probably half of you are freezing. Okay.
You can put the temperature a bit like 1 or 2 degrees down or less.
You think I should lower it?
I think you can try. Maybe you please complain if it's too cold.
Yeah.
It's okay.
Okay, I did 2 degrees. Let me know if it's too cold.
You are doing all the work, so it's okay.
Yeah. Okay. So in the puncture model, instead of having parametrizations of the boundaries, you have non-overlapping maps into the surface. So you can imagine, actually, I have some confusions about the definition in the literature, but if you want it to be equivalent to the Segal border parametrization model, you have to do what I'm about to do. So I'd like to talk to people about that if anyone's interested. So now instead we take R as a genus G surface with n punctures. And I'll try to keep my letters consistent. So if it's bordered, I'm going to use sigma, and if it's punctured with no borders, I'm going to use an R. So the punctures, you can also think of them in marked points because quasi-conformal maps and conformal maps always extend, so it doesn't really matter what you call them. So what we say, David and I came up with this rather horrible notation, and now we're stuck with it. So we call OQCR. I guess we were thinking of germs of quasi-conformally extendable conformal maps. I don't like it anymore, but too late. So these are maps from D into the surface, satisfying a bunch of conditions. So they should take 0 into the punctures. They should be conformal. And they should be quasi-conformally extendable. I should be precise about that, to an open neighborhood of the closure of the disk. And then also, we want that the closures of the intersections do not intersect. Okay, I guess I'll close the bracket over here. And the picture is, now instead of having boundary parametrizations, you have some punctures and a number of mappings, and they'll map onto jagged domains because we're not demanding much of the boundary behavior of these things. Okay, so any questions about that picture? Okay, so now how can you go between the two? You want to just sew on disks. So if you start with a bordered surface, you can sew on disks with the boundary parametrizations, or conversely, you can just rip out the existing images, and then you can go between the two models. So, but first I need to define the puncture model carefully. I've only defined non-overlapping mappings. Oh, right, sorry, I want to say something here. Theorem. When did we do this? OQCR is the Banach manifold. How do you model it as a Banach manifold? If anyone's curious, I can tell you, but maybe I'll skip that and just try to draw pictures instead. In function theory, it's there's not much choice about what you want to do.
So here you only require the quasi-conformal extendable to the open neighborhood.
That's right.
Then is this case the quasi-conformal extension unique to our?
No, that's not unique, but it is unique on the boundary. So it is
boundary.
unique on the circle.
On the circle it's unique.
Yeah, that's right. So somehow it's one of the natural analytic completions of the space of smooth things. So, and then there's actually many possible choices, and honestly, there might be different reasons to use different ones. Another thing I'd really like to talk to people about, but I've been thinking about that for a long time. But certainly for some things, Weil-Petersson is right, and then for the connection to Teichmüller theory, the quasi-symmetries are right. Or the initial connection, I guess. The classical picture. So now, puncture model. Of the Segal moduli space. we have the following definition. So we take m tilde p now. So this is genus G with n punctures. The p is for punctures, just for lack of a better name. So now you look at the setup R, it's called an F, moduli equivalence relation, where R is genus G n punctures. F is in OQC of R. And we say that two are equivalent. You can probably guess at this point. Here's just a sigma from R to R prime, which is conformal, which takes the non-overlapping map to the, which takes one set of extra data to the next set of extra data. And so now you can imagine there's some connection between these two. And so this is sort of implicit, or sorry, implicit is the wrong word. I'm starting to get a bit tired. This is in the folklore, so to speak, and I don't know who sketched it first. I'm sure someone here knows better. So we can define this cap mapping. So you take, so from the bordered surface picture to the punctured surface picture. And what you do is you just sew on discs. Oops. Okay, let me just define this. I just wrote some symbols in that obviously explains nothing, but I want to use a picture because formally it's a bit annoying. So essentially you just sew on the caps using the riggings, and you can do that in the quasi-symmetric setting by kind of souped up conformal welding. David and I showed that you can sew surfaces together using quasi-symmetries, and for many years that was the only citation we could get of our results, which is actually kind of the easiest thing we did. So you sew on the caps using your feeds, I'm using some version of conformal welding. I won't worry about it too much. It's not hard to do if you know about conformal welding. You end up in this picture. Now, strictly speaking, what you do is you identify boundary points using the riggings. Then you just glue the caps on topologically. Then you ask for the unique Riemann surface whose complex structure agrees with the complex structures on the two sides. And then you get a compact surface with punctures. The punctures are just the images of the disks under inclusion. And now what happens under conformal welding is you get now conformal maps into the uniformized surface. Now, if you construct this formally, these maps are just inclusion of the disk into the surface. So it's a little bit confusing. On one side, it looks like the identity, and on the other side, it doesn't look like the identity at all because you have this weird boundary identification. So I'm using this picture because it's clearer. It's better to mentally imagine. You uniformize to get the new surface. You get some weird jagged boundary curves here. And now these inclusion maps are conformal maps.
One more.
What's that?
One more map.
No.
So do you know what type of a boundary curve after uniformization will be like?
The quasi-circles.
Quasi-circles.
Yeah. So, and then actually, this funny thing is you can't find a definition of quasi-circle on a Riemann surface in literature. It's probably out there somewhere, I just haven't found it. But you do the obvious thing that you take a chart that surrounds the curve, you map it into the plane, and you ask that that's a quasi-circle in the plane. And you know, that whatever definition you come up with, it has to be that, equivalent to that. Okay. Yeah, I think I can get to the correspondence. Just thinking about the timing. I'm not stressing Sid, I just want to calculate what I should do. No. Right, so I want to talk about the relation of this to the Teichmüller space. But before I do that, I have to define some modular groups. So and if you're used to sort of the finite dimensional Teichmüller theory, there are some relations, but these potentially can be bigger groups. I'm still going to use R to be genus G and punctures, and sigma to be genus G and S1 borders. So, okay, this is a little bit technical, not too technical, but let me just say what I'm going to do before I do it. You can make a quasi-conformal deformation of the original surface, the base surface, and that's going to act on Teichmüller space because you can always pre-compose with this quasi-conformal deformation. This is just like if you're used to thinking of the finite dimensional spaces, that's just like the modular group that acts on the space by permuting some internal homotopy basis. But now these can also perturb the boundaries. So we want to talk about that action very carefully. So let me just define it carefully. I put PQC here of sigma. This is a set of quasi-conformal self-maps of sigma. And it's meant to be surjective and injective. I guess that's part of the definition. But it should preserve the boundary order. Okay? And that's what the P is for. It stands for pure. And so this matters. And then also, for the punctured one, same deal. Has to preserve the puncturing, the labels of the punctures. Okay? And I just need to mod out by the trivial ones. So you want to mod out by those which are homotopic to the identity because their action is going to be trivial. So now, write down the trivial ones. So PQC0 of sigma that's those that are homotopic to the identity. Row boundary. So that means it has to be the identity on the boundary. And same thing for the punctured surfaces. And this can be done all at once if you like, but I'm trying to like invoke a picture by separating them out. But if you think about it, the homotopy row boundary condition becomes vacuous in the case of punctures because we're already preserving the ordering, and that's all you need. And so now finally I can say P mod dot is PQC dot mod PQC0 dot. So mod stands for modular, P stands for pure because it's preserving the ordering of the boundaries of punctures. And so this acts on Teichmüller space. For example, in the sigma, did you have a question or no? So if you have this acts on the Teichmüller space, say if it's T of sigma, the action is just rho on sigma F sigma 1 is sigma F of rho inverse sigma 1. Okay. Now, if we were going to go to the classical theory, so just maybe make a remark here. If I were to remove the pure, just mod out by the modular group, this is now isomorphic to the Riemann moduli space. So, okay, but we don't want to go down all the way to the Riemann moduli space. We want to get the Segal moduli space. So if I did everything well, probably I didn't, but if I did, then you might even be able to guess what I need to do in order to mod out, find a subgroup of this modular group that's going to give you the Segal moduli space. So maybe, I don't know, I'm going to start writing, maybe somebody will guess. If you guess, yell it out. It'll be fun. So P mod I, maybe you're guessing what this is. Cool. So we're looking at the set of rho in P mod such that rho, the representatives are the identity on the boundary. It's almost inevitable. So, and I just want to make a note, if you do P mod R, it automatically fixes the punctures. Because quasi-conformal maps extend to punctures. So we have a theorem. So P mod I acts properly discontinuously and fixed point freely. One almost thinks this should exist in the literature, but we weren't able to quite find it, so we had to fill it in. But I don't know, if anyone ever finds it in the quasi-conformal setting and gives me this theorem as stated, I'd be happy. And now maybe I can draw a picture. Yeah, I'm going to draw a picture. Maybe it's better to put it here. I don't want to erase too much yet. No, I need a big picture. More of a diagram than a picture. So this is now the correspondence between Segal and Teichmüller. So let me draw a picture. So we have some projection here. And then we have, which way does cap go? This way. So let me say what the maps are. So maybe this one is the easiest one to say, this border model. So what we do is we fix a parametrization tau of the boundary of sigma. So just like in Teichmüller theory, we have to pick a base space. So in the Segal moduli space, we have to pick a base parametrization. So in order to make this work. So actually these maps depend on that choice of parametrization, but then that's much like in the case of Teichmüller spaces. The spaces themselves implicitly depend on the base surface, but you can always find a transformation when you change the base point. So it turns out this is inessential, you don't have to worry too much. So PB tau of sigma f sigma 1 is equal to just sigma 1 f1 of tau. So you just compose a quasi-conformal map with the base rigging. That's all you need to do. That's a very natural thing. And the other one P tau P. It's a little bit more complicated. I just want to draw some pictures. So let our tau be obtained by sewing on caps. So be a tau. So in this picture we have save the pictures for a minute. draw it now. And then you do something quite similar to the burst trick. So I'll call it a generalized burst trick. So given sigma f sigma 1, let f sub tau be from r tau into a new r, given by mu of f tau is equal to mu of the original map on sigma, and then 0 on these caps omega here that you get after summing on. So just like the burst trick, so now you have a quasi-conformal mapping that's on the entire surface, and when you restrict to the disks, now when you restrict to the caps, we have a new deformation. I'm running out of time, so I'm just gonna say p tau of sigma f sigma 1 is r. Let's call it r1 f tau composed with tau. So that gives us a puncture model. That gives us a puncture model element of the Segal moduli space. I'm running out of time, so then next time when I start, I'm going to recap this and draw some nice pictures. But I just want to say, the punchline of this. I just want to say the punchline of this. So first of all, this diagram commutes. All of these maps are well defined, which is not entirely immediate, but it takes some work. And then we have this is also David and I. We have that PB tau of P equals P tau B of Q, if and only if P is rho Q for some rho in P mod I. So this is exactly what you have to mod out by to get the Segal moduli space. And then remember I said these things act properly discontinuously and fixed point freely. They also act by biholomorphisms. So this is not our result. This is in the literature. It acts by biholomorphisms on Teichmüller space. So corollary. Well, we can write the Segal moduli space as just the quotient. And you have a bunch of consequences. So for example, I'll just say one of them and save the rest for later. It's a complex Banach manifold. So M tilde B N is a complex Banach manifold. So that's the first consequence for CFT of this Teichmüller theory, Segal moduli space correspondence. Okay, I better stop. Any questions?